Hello and welcome. Today we are going to tackle the first topic in Chapter 2, Polynomial Power and Rational Functions. So, in the past, we already talked about the basics of precalculus from the different 12 function, the basic 12 functions, to the modeling with the various functions that we have. But for this chapter, we're going to be tackling polynomial power and rational functions. This particular video will be tackling linear and quadratic functions in modeling. So that's what we're going to do today. So linear and quadratic functions, this should be easy cake for everyone because it's one of the first things we discuss in algebra, and linear and quadratic functions should be a familiar territory to most of you, and this should be a good start. So for polynomials, basically polynomials are one of the most familiar forms of functions that we have in math. Well, honestly, it's one of the easiest ones to tackle and one of the easiest ones to understand. So we're starting with that. So when we identify polynomials, we have to understand the notation that it's following. So basically, a polynomial is defined by its largest or the biggest power that it has in its dependent variable, which is usually the x. So in this case, if you have this format over here and you look at the a sub n over here, this is what we call the leading coefficient. The leading coefficient is basically the number or the value that's right next to the highest power of x or whatever variable is in there. Next, we have the n over there, and that's called the polynomial power. Basically, for your polynomial, for you to identify what kind of polynomial it is, you gotta know what's the highest power that it has. So let's go for an example. Which of the following are polynomial functions? For those that are polynomial functions, state the degree and leading coefficient. For those that are not, explain why not. Okay, so we have these functions for us. So we have 4. Let's start with the first one. F of x is equal to 4x cubed minus 5x minus 1/2. Okay, just by looking at this, we know that there's a specific power to it, the highest being 3, and there is no other different kinds of power that's on the variables. In this case, I would say that this f of x is a polynomial function of degree 3 with a leading coefficient of 4. Okay, but what if the example goes like this? What if we have a number that's a negative for the power? In this case, g of x is equal to 6x to the fourth, to the negative fourth, plus 7. Okay, the thing about this is that if you have a power that's a negative, you're basically converting it into a asymptote. In this case, the equivalent function of this g of x is 1 over 6x raised to 4 plus 7, and that gives you an asymptote. So in that case, this is not a polynomial function. It's a different one, and that kind of function we will tackle in the future. And because of the exponent negative 4 over there, it rendered our function not a polynomial. So always remember that not all functions are polynomials, and you gotta pay attention to their powers. Let's go for our next one. We have a square root. So h of x is equal to square root of 9x to the fourth plus 16x squared. Okay. Sometimes this may or may not be a function. It depends on the situation and it depends on the value inside. Now, if you look at this, sometimes there are perfect square polynomials. We can do that. If you do that and you're able to reduce your polynomial into its more basic form, then yeah, it is a polynomial. But in this case, h of x is not a polynomial simply because it can't be simplified into a polynomial form. Let's look at this. If we try to expand, or if we try to carry out the square root function into the whole term, this will not be equal to 3x squared plus 4x, which is the square root of each of the term. That's not the case. If you do this, it's a wrong It's a wrong process. It doesn't equate to that. So it's not a polynomial. How about this one? For this one, we have 15x minus 2x 4. This is obviously a polynomial of degree 4 with a leading coefficient of negative 2, only because the powers of the polynomials are real and positive numbers. The moment they become negative numbers, the powers, your polynomial will not be a polynomial. It's going to be something else. And we will tackle that in the future. Okay, so first of the polynomials, the simplest one, we've been doing this since since algebra, are linear functions. So basically, technically, linear functions are polynomial functions of degree 1. So there's the highest degree of 1 in a linear function. Okay, cool. Now, in this case, the form or the standard form for a linear function is in this format or in this syntax: f of x is equal to ax plus b. And sometimes in studying linear functions, we know that there is something called a slope that is a value inside the linear function. Now let's replace a with an m as the slope, and we're going to end up with this formula. So this is something that's familiar to everyone. This is called the slope-intercept form. So this is one of the most basic formulas for linear functions that we use because it's really useful. It tells us how much the function is increasing or decreasing and what's the slope or what's the behavior of this graph. So this is called the slope-intercept form only because of this. The m over here is our slope and the intercept will be the b over there. But also, if you notice, the b is also the y-intercept. You can prove this by equating x to 0, and you're going to get y as the b only. So that's the y-intercept. How about for the linear formulas? Just a review of algebra for us. The slope formula will be the change in y over change in x, or the rise over run. And in terms of formula, it's going to be in this form. This is actually a very important formula because most of the slope in linear formulas came from the slope formula. So that's something to think about. For the slope-intercept form, this is something that we know. This is y is equal to mx plus b. The point-slope form, when you have m, a slope, and a point xy, is this formula. Y minus y1 is equal to m, quantity x minus x1. Let's try to apply this into a problem. Okay, so write an equation for the linear function f such that f of negative 1 is equal to 2 and f of 3 is equal to negative 2. Let's try to find out. So the first of the functions, or the first here, is f of negative 1 is equal to 2. Just by looking at it at first, we might not see that this is actually another way of writing the points for us. So if we pay attention to the f of negative 1 over here, this is just a translation of f of x. So you're basically just putting in a value for x, which is negative 1, and try to get y. So f of x is also y, and it's also equal to 2, which is that number over there. Okay, so once we have that, let's focus on the negative 1 inside. So remember that this is actually just following the syntax of f of x, which means that if x is equal to negative 1, our y is equal to 2. So that's what this means. Okay, so let's try to find out some more. So in this case, our x is equal to negative 1 and y is equal to 2. In turn, the first point will be negative 1 and 2. Let's try to get the other one. But first, let me show you where this came from. The negative 1 came from the value inside the f of x, and the 2 is that other one outside. This is correct. Doing the same thing, we can get the second point, which is 3, negative 2, and that is this and that. That's how you get these points. Now that we have our points together, it is time for us to, to assign the value of x1 and y1 and x2 and y2. Honestly, you can apply or you can assign these notations to any points that you want as long as they're x and y. It doesn't matter which one is first. You'll see that. You'll see it when you try it. But first, we got to get the slope. For us to get the equation for the line function, the slope is one of the most important ones. So formula is equal to y2 minus y1 over x2 minus x1. With this one, let me show you that we just have to put in the data. So the first chunk over here came from the x2, y2, because y2 and x2 comes first, minus the other chunk, which is negative 1 and 2. Doing this together will get you negative 1. So the negative 1 will be the value for the slope. So we know it's a decreasing slope. Now, since we have m, which is a great thing, and we have a point negative 1 or negative 1, 2, we can now try to put this into the point slope form, actually. So this is the slope, this is the point, and we have both of them now. Let's try to use the point slope form in this formula. Putting in the data for the points and the slope, it should look something like this. Simplifying, you're going to end up with y is equal to negative x plus 1. So that's how you get the equation for a linear function. So much for a review. This is something that you should know from last year's algebra. Okay. So let's talk about something called the rate of change or average rate of change. In calculus, this is something very important because the idea of slopes and change in y and change in x is something very important in calculus, actually, that I have to introduce to all of you what average rate of change means, at least in passing. So basically, the rate of change is the formula, the slope describing the change in y over x. And we know that to be this formula. And actually, we gotta dissect or we gotta digest more what the formula means. So the slope formula is describing the changes in y over x. So we have delta y over delta x. The good thing about here is that in this form of the formula, you're going to see that the y changes as x also changes. That could be useful when you have problems or other applications of changes in rates. So that's why we have that. So the rate of change of a linear function slope m is constant. So always remember that. If you have a linear function, the slope will always remain the same for all points. So sometimes the slope is also called the rate of change of the linear function. So if you encounter a formula, if the formula didn't mention slope, they might mention rate of change or sometimes even regression. It really depends on the kind of questions or problem that you're presented. Let's go for an example again. Camelot Apartments bought a $50,000 building and for tax purposes are depreciating at $2,000 per year over a 25-year period using a straight line depreciation. So there. What is the rate of change of the value of the building? Write an equation for the value of v sub t as a function of time t, and evaluate v of o, or v of 0, and v of 16. Okay, let's try to analyze this question first. Let's try to answer the first question. What is the rate of change of the value of the building? First, there's a clue word in the question, and that is something mentioned here. It's depreciating $2,000 per year. And that is actually, it indicates a negative slope or a negative rate of change. It means that our slope is decreasing. So we have an m, and it's going to be negative 2,000. So that's cool. We already have the slope for us. First question answered. Now, next one. Write an equation for the value v of t as a function of time t. Now it's asking us to write the line equation for the whole thing. Now using this function over here, or this syntax, or the formula for slope-intercept form, we have y is equal to mx plus b. And putting it together, our b is 50,000 because we started with the value of $50,000. Now it's going to depreciate 2,000 times time. So this is the new equation for the line. So next, the third equation. Write an equation for the value v of t is a function of time t. So when we need to evaluate v of 0 and v of 16. So basically it's like this. You just have to put in the value if our t is equal to 0 and our t is equal to 16. Let's start with 0. When our time is equal to 0 at the beginning, our slope non-existent, 2,000, negative 2,000 times 0 plus 50,000. So our y will be 5,000. Okay, so next is the time. When our time is equal to 16, we just put it in, and our new value after 16 for time is 18,000. All right. So there's another thing that we need to understand from the way line behaves, and that's something called correlation. In statistics and other fields, the correlation is basically us trying to understand the description of the linear association in a plot, aka this is how much your points resemble a line. For you guys who have handled scatter plots already, sometimes your points in the graph will resemble some sort of line or curve. Sometimes the easiest way to build a correlation with that is with a line of best fit. Now, with the correlation with here, I'm going to show you this drawing or this illustration. Now we have a scatter plot and we have some points over here. They are vaguely resembling something. And I drew, there's an oval here, an ellipse, showing us the distribution of this data. Now, first we have a thin oval, which is very thin. And if you see the relative slope of the whole thing, we can see that it's suggesting a positive slope, and therefore this is going to be a strong positive linear association. Only because your points are closer to the line of best fits. The closer they are to becoming a straight line, the better. Now, if you have something like this, the oval is a little bit rounder, a little bit fatter. So, and it's still suggesting a positive slope. We can still consider this a linear association that's positive, but it's weaker. So we have a weak positive linear association. So that's what happens when it's a little bit farther away from the line of best fit. Now for the other end of the spectrum, we have this. You have a distribution of points over here, and they are vaguely resembling a line. But this time they are decreasing in y while they're increasing in x. So in this case, if you draw an oval, you have a thinner one. And this can tell me that this is strong negative linear association, only because you can see that the points are closer to the red line that you see on the illustration. Now, in the case of something like this, a fatter oval or a more sparse distribution of the points, they're farther away from the original, not really original, but the line of best fits. This is going to give us a weak negative linear association. And lastly, if you have a scatter plot like this, and there doesn't seem to be any pattern that you can make out, not even other forms of lines, then we can say that this scatter plot or this distribution of data has little or no linear association whatsoever. That happens sometimes, and that's up to us to identify. Moving on, we have quadratic functions. For quadratic functions, this is the second of the polynomials that we discussed in algebra, or you tackled in algebra in your time. And these are polynomials of degree 2, and we know this. And the parent function goes y is equal to x squared, or f of x is equal to x squared. And this will give us a parabola. Now, if we try to get the standard form for this, this is going to be ax squared plus bx plus c. The vertex form, this form is really great for telling us where the parabola starts. So that's the vertex form with y is equal to a quantity of x plus or minus h squared plus or minus k. Now our vertex will be the value of h and k, and the axis of symmetry will be y is equal to negative b over 2a. The axis of symmetry, this will be the value for our sorry, this should be x minus negative b over 2a. This will be the value for x. Let's try to apply this into a problem. Use completing the square to describe the graph. This graph. Y is equal to 3x squared plus 12x plus 11. Now, look at this. So we have to isolate the x with 3 quantity of x squared plus 4x plus 11. So I took out the x, I isolated them, and I took out the 3 because it's easier to complete the square if your x squared has just a 1 in it. So by doing this, you can see that here, as the arrows are pointing at, in order for me to complete the square, which is x squared plus 4x plus 4, I have to add 2 squared, and I also have to subtract 2 squared. And these are called nullifiers. So the nullifiers are basically just you adding 0 to the whole equation, but at the same time enhancing the other parts of the equation in such a way that you can perform a task. In this case, you can perform completing the square. So basically, we added a 0 because 2 squared minus 2 squared is still a 0. So I added nothing to the equation. So taking out the 2 squared while multiplying it by 3, we're going to get 3 times 4 plus 11. So we take out the nullifier and we're going to end up with y is equal to 3 quantity x plus 2 squared minus 1. So that is the vertex form. And we can now simplify and we can now describe this. So this is a parabola opening upward with a vertex of -2 and -1. Let's have another one. Use vertex form of a quadratic function to find the vertex and axis symmetry of the graph f of x is equal to 6x minus 3x squared minus 5. Okay, let's try to understand this. If you have a quadratic function in this form, all you have to do is to just rearrange them into the standard form. So if I do that, it's going to be -3x squared minus 6x plus 5. So that's fine. In this case, we can now match it up. We know that this is based on the standard form of the quadratic function, and we have a is equal to -3. We can see it there. We have b is equal to 6 and c is equal to -5. Now, all we need to do is find the axis of symmetry. The axis of symmetry, the value for x in that one will be the x in the vertex. So that's why it's very important. Now, let's try to do this. So our function is, or our formula is h is equal to -b over 2a, and inputting the value of the required, it's -6 over 2 times -3. And this will give us a value for x is equal to 1. And this is going to be the h in the h of k. Next, we need to see here that our k is still missing. We got to know what that is. But now we have an h, which is 1. So it means that we can now use 1 and k. We can use 1 to get the k. Now, if our x is equal to h is equal to -1, from y is equal to -3x squared plus 6x minus 5, we can put it in now. K is equal to f of -1. It's equal to -3 times -1 squared. Sorry, 3 times 1 squared plus 6 times 1 minus 5. So our k will be -2, and our point for the vertex will be 1 and -2. So that will be our point. So the vertex of the parabola, as we can see here, will be inputted into the vertex form, which is y is equal to a quantity of x plus minus h quantity squared plus minus k. Just inputting the formula, we know a already from before, it's -3. It's going to be this form. And that's how you get the vertex form of a quadratic function.